Hi everybody. Today we're getting started integrating logarithms and exponential functions. Let's start with the formulas that we know for derivatives. The derivative of e to the x is e to the x, and the derivative of ln of x is 1 over x. We have two other formulas. They get used a little bit less frequently. They're for more general exponential and logarithm functions. The derivative of b to the x is b to the x ln b, and the derivative of log base b of x is 1 over x ln b. So every time you have a differentiation formula, you have an anti-differentiation formula. Or to say it differently, a formula for an indefinite integral. So taking those first two formulas on top and anti-differentiating both sides, I get the integral of e to the x dx is e to the x plus c, and the integral of 1 over x dx is the natural log of x plus c. Now, here and elsewhere, you'll see absolute values around the x in natural log of x plus c. And this is because the domain of natural log of x is only the positive numbers, while the domain of 1 over x is all real numbers except 0. So putting in that absolute value sign on the right gets you a slightly more general answer than if I just put ln of x, one that also applies for negative values of x. We also get anti-differentiation formulas for the other two formulas with the base b, but only one of them is really needed. The integral of b to the x dx is b to the x over ln b plus c. If you need to integrate 1 over x ln b, you can just do it using a natural log. You don't need a special formula for that. So there are three new formulas for anti-differentiation here. The first two, of course, are the ones that are most important for most applications. Let's do some practice. The integral of e to the 8x dx. So I know when I anti-differentiate e to the x, I should get e to the x. So here I'm expecting something like e to the 8x. However, if I differentiate e to the 8x to check my work, I end up using a chain rule and I get an extra factor of 8 that I don't want. So I have to compensate for that with a factor of 1/8. Now when I differentiate the right-hand side, I get e to the 8x, the integrand that I started with. Let's do a slightly harder one. Let's integrate secant squared of x e to the tangent x dx. This one we'll do with a u substitution. We'll let u be the inside function, noticing that the derivative of that inside function appears as a factor in our integral. So when I say u equals tangent x, I get a derivative of secant squared, which I then solve for dx. Dx equals du over secant squared of x. My next step is going to be to plug in u where I see tangent, and to plug in du over secant squared x where I see dx. There we go. This is what it looks like. Now I get a nice cancellation. The secant squared in my integrand cancels with the secant squared in the denominator that I got when I differentiated my u substitution. And I'm left just with e to the u du, which is the easiest thing in the world to integrate. I get e to the u plus c. The last step is to take out u and replace it with the function of x that I started with, e to the tangent x plus c. One more quick example. Let's integrate 3 to the x plus 2 dx. There's several ways to do this. We could do a u substitution. I'm going to do it just by using the laws of exponents. 3 to the x plus 2 is 3 to the x times 3 to the second, 3 squared times 3 to the x. Factor out the 3 squared and integrate the 3 to the x. I get 9 times 3 to the x over ln 3 plus c. That 9, of course, is 3 squared, so I'm going to rewrite the 9 times 3 to the x as 3 to the x plus 2. So there's my final answer. Let's do a few problems using the other anti-differentiation formula we learned. The integral of 1 over x dx is the natural log of the absolute value of x plus c. Let's start with the integral of the natural log of x to the third over x. So this is another good candidate for a u substitution. We have an inside function, the natural log of x, and the derivative of that inside function is a factor in the integrand, namely 1 over x. So we set u equal to that inside function, differentiate both sides, and solve for dx. Then we substitute in to get the integral of the natural log of x to the third over x is the integral of u to the third over x times x to u. The x's cancel, and I'm integrating u to the third to get 1/4 u to the fourth plus c. Taking out the u and replacing it with what it's equal to, 1/4 natural log of x to the fourth plus c. Example 2. Integral of x cubed over 1 plus x to the fourth dx. It's another u substitution. U equals 1 plus x to the fourth. Differentiate to get 4x to the third. Solve for dx. Replace the 1 plus x to the fourth with u. Replace the dx with du over 4x to the third. And cancel. Now we're looking at the integral of 1/4 du over u. And of course we get 1/4 natural log of the absolute value of u plus c. Last step as always, take out your u, replace it with what it's equal to. 1/4 the natural log of the absolute value of 1 plus x to the fourth plus c. Now, in this case, 1 plus x to the fourth is always going to be positive, so we don't necessarily need that absolute value in there. If we wanted to just put in parentheses, we could. One last one. We want to anti-differentiate our old friend, tangent of x. So we're going to do this one by writing tangent of x as sine of x over cosine of x. When you're doing calculus, that's usually a good thing to try. There's a good u substitution here. U equals cosine of x. Differentiate to get negative sine of x. Solve for dx. Dx equals negative du over sine of x. And plug back in. So I take out cosine there in the denominator and replace it with u. I take out dx and replace it with negative du over sine of x. The sine x's cancel, and so I'm integrating du over u, which is, of course, the natural log of the absolute value of u, plus c. Take out u, replace it with what it's equal to, cosine of x, and we've got an answer. Now, if you look in a table of integrals, this won't actually be the thing you see. You will see natural log of the absolute value of secant of x plus c. What's going on here is that they've taken that negative sign in front of the natural logarithm, moved it inside the natural logarithm as an exponent, the natural log of the absolute value of cosine of x to the negative first power, 1 over cosine of x. And of course, 1 over cosine of x is secant of x. So that's why the answer is equivalent to the natural log of the absolute value of secant of x plus c.